I audible? Okay, so let me start with the discussion. So the first question, uh, Arnav is there. Arnav, can you tell me whether you have attempted this question?
Yes, I have attempted it.
Can you share the approach? What approach you use?
Yeah, so first I checked whether we should be reforming the actual set of array or not by checking every element at the similar index of both A and B. Then after reforming is basically we sort both array A and array B as elements will be uh, put together, which in order that array A has bigger elements and array B has smaller elements, and then check. If we get any element in array A that is smaller than array B after the sorting, then we know that it is not possible. And if we do get after reforming, then it's simply the sum of A minus sum of B plus C seconds that it took to reform. And if reforming does not take place, then it's simply sum of A minus sum of B.
Yes, so you have done the approach. Okay, so since you have done the question without reading the entire question, let me summarize quickly. So here the problem statement was telling what that we have been given two arrays A and B of length n, and our goal was to transform A into B using the two operations. That is, uh, operation one was either we can choose an index I, and we can only decrease ai to ai minus 1. Okay, so there was no option of increasing. This is another important point which we need to keep in mind here. And another, and this will cost again 1 second. And another uh, operation was we can reorder the array in any way. So this cost c seconds, uh, which has been given in the question. So here in the first test case, you can see this is n and this is c. So as you have already told your approach, so the key observation is that we can only decrease the values. We cannot increase any value. Okay, and reordering is optimal and can be done whenever we want. Okay, so the intuition is that uh, um, uh, like we have two operations. We can either decrease one, we can either decrease the element by one or rearrange it once. And uh, reordering more than one is actually never useful. Okay, why it is not useful? Why only one reordering will work? Because after rearranging once, we will definitely place all the elements wherever we want, right? So uh, rearranging another, there like we don't have any point. Okay, so two options, uh, either not to reorder, and when are we not going to reorder? If array of a one element of uh, the eighth array is greater than the b's element. Okay, so then we don't need to reorder. Even if a single element of a is less than b, we have to reorder because there is no option of incrementing, right? There is no option of incrementing. So in that case, we need to reorder. Now, reordering the elements, uh, when do we, how do we rearrange? Our way is to rearrange such that we get the minimal cost. The cost is minimal, right? So, like we can do it optimally and place it like we can reorder such like the best way to reorder is to sort both the arrays. Okay, now the question is why we sort both the arrays, right? While reordering, why is it like best to sort both the arrays? See, our approach will always be what? To minimize the cost. So it's definitely we will match the smallest element with the smallest, the second smallest element with the second smallest, and the largest with the largest. That is how we will minimize the difference, right? So that is the reason we sort both the arrays. Okay, so uh, this is clear. And even and when is the impossible case happening? That even after sorting, if still any element of a is less than b, then it's impossible. We return -1. Okay, so you have already told the approach, and this is the code that if uh, anywhere a is less than b, then simply uh, uh, like there is no point uh, using this. We need to come here and we need to sort both, and then again we need to check that whether again then also any element of a is less, then it is f equal to -1, or else the difference plus c. Okay, and if uh, like this condition never happens, then only simply difference 1 we will return. Okay, I hope this is clear. Okay, now let me move on to the next question. Next question, have you done?
No, I can't solve it.
Okay, okay, so let me explain. So this question is what it states is that there are n 1 to n numbered i's. Okay, 1, 2, 3. Okay, so you have to count the number of ordered triplets. Okay, that is a b c, such that this condition is valid. Okay, and also repetition is allowed. It's mentioned here. Okay, but order matters. uh, like a1 b1 c1 and a2 b2 c2, they are considered different if uh, a1 is not equal to a2, but like within this repetition is allowed. Okay, and this is the main prime condition. Okay, so now you can see the test case also. uh, and for n equal to 1, the answer is 1, and n equal to 2, the answer is 5, and these are the orders. Okay, so now let me explain. First, see this condition. Okay, now when you see this condition, you can see that b is common in both. Okay, so uh, like we can find for which pairs LCM of a comma b equal to a and LCM of b comma c equal to c, then only this equation will satisfy. Okay, now okay, wait, let me show you.
Wait for a few moments. I think it's a network problem. Okay, so till then, let us first discuss the problem C and D. I hope the issue will get resolved at that time. Uh, since D was kind of easier than C, and C involves some graph aspect, so let us first discuss the D problem. So it will be easier to understand, I hope. Okay, am I audible and is the screen visible? Right, okay. So this was the D problem. Have you solved it? Storming Arasaka.
No, yeah, I couldn't.
Okay. So it's in like the problem statement is easier. You can like read it. Okay, first I'm reading it. Okay, so it is given a okay. So you were given only a number n, and you have to play with its divisors. So what we have to do, partition all the divisors into several non-empty layers, okay, L1 and 2 Lk, and a partition is called good if two conditions are satisfied. That is for any divisor fx, that is a divisor of n, all its divisors except 1 and x lie in the layers L1 to Li minus 1, that is below layer Li, and each layer all numbers can be ordered into a chain so that any two neighboring numbers have GCD greater than 1. Okay, so let us understand with a example. Let me use a darker color. Yeah, n equal to 36. Okay, what it trying to say that, okay, we have to like play with its divisors except one, so its divisors 36 can be prime factorized as 2 square into 3 square. Okay, that is 4 into 9, 36. So its factors are basically 2, 3, 4, 6, 9, 12, 18 and 36. Okay. I hope I am not missing any factor. Yeah, I'm not missing any factor. Okay. So basically, you have to partition these factors into several layers. So I'm making some layers. Okay. So these lower layers are starting from L1, L2, and then goes on like this up to Lk. So you have to place these uh, factors in those layers, and two conditions must be satisfied. So the first condition is said that, okay, so if any factor, suppose I'm placing this factor in layers such as Li, 12, I'm placing 12 here. So the all its divisors, that it is clearly written that all its divisors except 1 and x, that is 12, it must be in the layers L1 to Li minus 1. That is all its divisors as is 6, 4, 3, 2. They must be present in some lower layers. So let me place 2, 3, 2 and 4 here, 3 and 6 here. Okay, like that. So this is my first condition. Second condition is that, okay, so in a particular layer, I have a string of numbers, and suppose I have a string of numbers a1, a2, dot 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 ai minus 1, ai. So for every ai and minus 1 and ai, its GCD must be greater than 1. Okay, so let me check. Is Can you tell me, is this a valid condition? Whatever I have partition, is it? Are you sure? Are you sure? Okay. Whatever I've told that all its divisors must be below it. You can clearly see here. If I Can you see the 4, and is 2 is a divisor of 4? Am I
Yes,
right or
yeah.
wrong? So it must be placed below it, no? So this
Yeah.
is an invalid. Okay. Same for this one. I'm placing 6 here, but 3 must be placed below it now. Right.
Yes.
So this partition is invalid. Okay. Let me try some more. Okay, let me get the solution for, okay, let me take a small number n equal to 12. Okay, so basically factors at 2, 3, 4, 6 and 12. Okay, let me place that. Suppose I place 2 here, 3 here, 4 here, 6 here, and 12 here. Is this now valid? Okay, is this now valid?
Yes, we are.
I think so. It is valid. Let me check. Okay, if it they are okay, they are single. No worries. All the divisions of 4. Okay, below it, all the divisions of 6. That is 3 and 2 below it. Okay, fine. And their GCD is 2. That is greater than 1. And 12. Okay, uppermost all the divisions. So this is a valid one. Okay, so in this way, my answer would be basically 4. Okay, I have to find the minimum number of layers I can partition this. So where it is written. Okay, for help join to define minimum number of layers, right? I have to find the minimum number of layers. So in this way, my 4 is the answer. Okay. Uh, okay, let me ask you some. Let us make some more observation. Okay. Suppose, okay, 36 can be written as 2 square and 3 square. Okay, so 2 and 3 are basically my prime factor. Can you tell me what are the maximum number of prime factors I can place in each layer? Suppose I have placed P, P is a prime. Can I place any more integer, any more prime number or anything? Anything, any
Uh,
composite prime, anything.
no, it should be a multiple. No,
Okay,
it
so
can't be
you are saying
multiple.
a multiple, so I can place 2p to get the GCD greater than 1. You are saying from this condition, but it kindly violates the
Yeah,
condition 1 because 2p is a divisor of 2p, right?
yeah, yeah.
So at max, I can place only one prime factor of in a particular layer, right? Particular
Yes,
layer.
man.
Okay, so one thing I'm getting sure is that whatever, okay, 36 contain two distinct primes in its prime factorization. So my answer would be basically contain m plus some layers. I will talk about it later. This m represents my number of distinct primes. Distinct primes. Okay, that is 2 and 3 here. Okay, now let you can see here I have placed 2 and 3 in separate layers. Okay, now let me talk about the composite factors. How can I place 4, 6, 12? Okay, these are my composite. Okay, composite factors or composite divisors. How can I place these? Okay, tell me one thing. What is the smallest composite number? What is the smallest composite number?
4.
4, yeah, 4. 4 is the smallest composite number. Okay, how many prime factors are required to make 4?
1.
No, 2. I need 2.
Oh, yeah, yeah, yeah.
2 into 2. For 6 also, 2 into 3.
Yes, man.
For 12, I need 3. 2, 2, 3. 4, 3 are 12.
Yes,
Right?
man.
Yeah. So you're kind of getting intuition. So after placing the lowermost prime factors here, so in this layer, I am placing those composite factors that are made up of two primes. That is 2 into 2 and 2 into 3. This is 4 and this is 6. Here I am placing that are made up of 3 primes. That is 2 into 2 into 3. Okay, you can get the total number of prime factor as 2 square and 3. Since this is 2 square into 3, so total number of factors will be sum of exponents. Okay, that will be 2 plus 1 3. Okay, number of primes I require to like make this. So the required answer would be something like this. So let I take m layers to place my distinct primes. Then here I place those composite which require 2, then 3, and let my n take k distinct primes in its prime factorization. Okay, this is my layer k. So my answer would be nothing but m plus, this is k minus 2 plus 1, right? This will be my required answer, right or not?
Yes, we are.
K minus 2 plus 1, so number of layers. So let us take another example to like, let us verify we are right or wrong. Oh, okay, what is 36? 36 is nothing but 4 into 9. 4 into 9 is nothing but 2 square into 3 square. Okay, so let me place. So I'm starting with 2. I place here 2, then 3, then the composite numbers which require 2 primes, that is 2 into 2, 2 into 3, and 3 into 3, that is 4, 6, 9, and adjacent GCDs are also greater than 1. Next, I place those which requires 3 prime, that is 2 into 2 into 3, and 2 into 3 into 3, that is 12 and 18. Then at last, since the number of total number of times is at total 4, 2 plus 2 4, so I at last place 2 into 2 into 3 into 3, that is 36, right? And in this way my required number of ways would be 5. Okay, one thing we'll notice that if n is a power of 2, that is for example 64, answer is basically the 2 to the power 6. The answer is 6. Why? Because for 64 I can place 2 here, then 2 into 2, then 2 into 2 into 2, then 2 into 2 into 2, and so on. So for 2 it's 1, for 4 the number of layers equals is 2, for 8 is 3, and you can see in the test cases also, yeah, 2 is 1, 4 is 2, 8 is 3, and so on. And in this way you can solve the question. Okay, great. Are you able to understand? Yeah, right. Okay, let me at last look at the code. Lot of, okay, I think, yeah. So basically, for this, first you need to, you should know the concept of SPF. I hope you know, or else this SPF is the smallest prime factor. So since the constraints were 10 to the power 5, yeah. So I have 2 into 10 to the power. I think no, I'm at the wrong question. I think, yeah. What is the T problem? Uh, I think, yeah, go here. Okay, so constraints were basically 10 to the power 6. So I have like pre-computed the things, the pre-computed all the smallest prime factor of each number. So in this case, you can see I have like pre-computed the SPF. SPF means smallest prime factor of each number. So the smallest prime factor of 2 is 2, 4 is of 4 is 2, for 8 it's 2, for 6 it's 2, for 9 it's 3, for 10 it's 2, and so on like this. So basically I use this SPF to calculate my uh, prime factorization. So I have taken VLL, this is pair LL, vector of pairs. So my answer would contain like this. For 36 it would, my answer would be like this. So since it is 2 square into 3 square, so it will contain 2 comma 2 and 3 comma 2. So from this I have like computed my Answer. So VLL answer is nothing but vector pair LL comma LL and like this. And LL is basically long so that I should not worry about any integer overflow. Okay, and my result is initially 1. So the size of array would be basically the number of distinct primes. Okay, so size of answer, this is my m value, and my result contains all the sum of all exponents. So these value would contain the result and then minus 1. Okay, in this way I computed my answer. Okay, are you able to understand the code? If you have the idea of SPF, you can like understand it, or else I will share the resource to like understand SPF. Right?
Okay, bhaiya.
Okay. Okay. What about C? Have you solved C?
No, bhaiya.
Okay, I think have you read tree traversal DFS BFS anything?
Yeah, I have read about it, but I
Okay,
have forgotten most of the part of.
okay. All that can be solved from DFS, but I have solved it using an iterative way. Let me like take that image. Yeah, right. Okay, so here basically what I have to return is that okay, for particular node, where is my for particular node, suppose this is my node 4. Okay, so what is a guild? Okay, consider the set of houses that are in the subtree of V at a distance exactly h from V. So let us consider this node is at a distance h equal to 0. Okay, this node from 4 I am looking to, this is a subtree of 4, subtree of node 4. Okay, so for h is equal to 0, single 4 is present, right? For h equal to 1 also, single 5 is present, but h equal to 2, with respect to 4, 3 nodes are present, 6, 7, 8. So my set will be, so required guild will be 6, 7, 8. Okay, let us consider this node. So for h equal to 0, simply 1 would be there. For h equal to 1, 2 nodes are there with respect to 1, 2 and 3. So this is my guild. And for h equal to 3, so only 4 is present, but I have already considered 4. So I will not consider 4. This is my overlapping. So I have my answer would be uh, what I want to know. Okay, how many different non-empty guilds are there in the tree? Okay, so I have to find the number of these guilds. Okay, what are the other guilds? Okay, so for each individual node, for each node is set of V is a guild. Yes or no? Uh, right. I'm
Yes,
saying
yes,
for
bhaiya.
yeah, because for each node I can consider h equal to 0, right? So for 1 to 8, so for 1 to basically up to 8, it is my valid guilds, right? Now to understand this question, let me reframe it. Okay, let me draw a tree. Suppose this is 1, and it is a children, 3 children, 2, 3, and 4. 2 is a height at 4, 2, 5, 6, 7. It has a height, come on, say 3, 8, 9, and it has a height, say 4, 10. Okay. Now tell me, I have already, in my guild, already these are present. from 1 to 10. These are only present. Okay, now I'm traversing. Let me traverse. Okay, so at a distance d equal to 0, I found this one. At d equal to 1, okay, for d equal to 1, I'm getting this set, that is 2, 3, 4. For d equal to 2, I'm getting this set, that is 5, 8, 10. For d equal to 3, I'm getting this set, that is 6, 9. But you will observe that at d equal to 4, I'm getting a single 7. So have I not considered already from 1 to 10? So I will not consider 7. So what you are getting intuition is that I am only considering for a particular node, I'm only considering sets up to the second max height of its child. So this child has a height of 3. Okay, so 2 has a height of 3, 3 is a height of 2, and 4 has a height of 1. So I'm only considering up to second max height. Why? Because to consider a particular set, it must have at least two children. Okay, must have at least two children. Why? Because suppose this is a node, and if it has only one children, I will not consider it because I have already like considered all individual guild set for d equal to 0. Okay, are you getting the intuition what I am trying to say? This 7 I have already computed for d equal to 0 and for node equal to 7. So for a particular node, I will only traverse up to that child that has the second max height. That is second maximum height. Okay. So my answer would be basically answer would be okay. Total number of nodes, that is n, plus the for a particular node second max height. Okay, for all b, that is for all children, I will consider for all nodes, I will like consider all its children and compute its height. Are you able to understand what I'm trying to say? Okay. Now let's look at the code. I think you will. Okay, one thing is there for our simplicity. This one can be treated as the tree is being rooted at one. I think it's written somewhere. Yeah, it is a represents a rooted tree rooted at vertex one. So my this node will be leaf node. By these nodes will leaf node. So the last node would definitely be a leaf node in the tree. Okay. So with respect to that, I have written my code. Let's see what I have written is yeah. In this you can see, yeah. So I've traversed backwards because I am going from top to bottom. So I need to calculate the heights. Sorry, I have to calculate the height. So it has a height of 0 since it is a leaf node. So I'm going through top to bottom. Okay, and kind of calculating the heights. Okay, so this is my adjacency list. So each parent, I'm pushing the child, and if the adjacency list is 0, that is it is a leaf node. Okay, it is a leaf node. So continue, I'll not consider it, or else I'm making two pointers to store the maximum and second maximum value. So this I've also maintained a height array, so it will store all the heights of the nodes. And yeah, you can clearly see like, okay, so what will be the height of one? It will be definitely be 1 plus let me change that, 1 plus maximum height height of its child. So in this case, since the height of this child is 3, so my height of 1 will be 4. 1 plus 3 equal to 4. Okay, I'll consider the max height of its child. So you can clearly see I have okay, so LLP is HK plus 1. Okay, so I've computed the maximum value, and yeah, then I update the maximum. Okay, and I have the maximum second maximum, and if it is not like it does it, if it has a second maximum, so I will increment my answer by maximum second maximum. And initially I have considered all the individual grid sets and then written my answer right at the end. So in this way, uh, I have like implemented this. Okay, you will be more clear when you will solve more questions related to tree and understand. Okay, so this is definitely a custom problem. How you can evaluate the height of each node. Okay, and okay, I'll share the resource if you need how to like practice question or not if you want. uh, if you're able to understand, you can say yes.
Yes, Bhaiya.
Okay. uh, okay, so I have discussed the C and D problems. Okay.
Okay. So, am I audible? So now let's continue with the B problem. Okay. So I had already summarized the problem. Now this was the condition, right? GCD of LCM of A comma B and LCM B comma C equal to GCD of A comma C, right? So uh, from this, it's very obvious that we can let LCM of A comma B equal to A. Okay, LCM of uh, A comma B equal to A, right? And also LCM of B comma C equal to C. B comma C equal to C. So if we are considering this, okay, now uh, now when will this condition be valid? Okay, when will this condition, when LCM of A comma B equal to A, when will this be valid? Like LCM, suppose I'm not writing, like LCM of consider B as 1. Consider B as 1. Okay. So now can you tell me that what can be the values of A if B is 1?
Any number greater than 1?
Yes, the multiples of 1, right? Yes. So
Yes.
it can be 1, 2, 3, 4 till n, right? Similarly, this works for this also, right? And B is common here, as I was telling. Okay. The same thing will work for this also. B comma C. Like the value of C can be 1, 2, 3 up to n. So suppose we have A, B, C. Okay. Uh, so keeping, if we keep B and C fixed, so suppose we keep B as 1 and let C be 1. Okay. So A's value, what can be the values of A you told? The multiples of 1 till n, right?
Yes.
Yes. Similarly, the case will work for these two are fixed, right? Similarly, this will also happen if A and B are, if we keep these two fixed and we uh, determine the value of C. Okay, B is common here. Suppose B is 1 and C is some fixed number. The number of values of A we got as K, and similarly for C also. Suppose if A is 1, B is 1, and C is value we need to determine. So similarly, all the multiples of uh, B till n, right, for C.
Yes.
So what will be the total number of possibilities? K into K. I mean total number of combinations. B is,
Yeah.
yes, got it? Yes, B is common. So we are varying A and C. The total number of possibilities K into K. So what we need to do is uh, we need to just find out the number of multiples, right?
Yes.
Yes. So this is what I have done. So you can see I have gone till for n equal to 1. Like I have gone till n plus 1. I equal to 1. I have gone till n plus 1. Okay. And I have multiplied. So this is your K into K. You're getting?
Yes, Didi.
Yes. So this is the code.